We're going to talk about inverse relations first of all. So inverse relation basically returns the dependent values back to the independent values. It goes back the other way. So here's two sets, A and B. So at this stage, minus 2 is going to 4, 2 is going to 4, 1 is going to 1, and minus 1 is going to 1. So it's y equals x squared could be a rule for that particular one. Now if I want to send it back, so now the 1 goes to both minus 1 and 1, the 4 is going to 2 and minus 2, then that would be y equals plus or minus the square root of x. Or I suppose another way I could say it is y squared equals x would return those numbers back. And that's what we would call the inverse relation. So A and C would end up being equal sets because we basically put everything back to where it came from. If you want to find what it is, if you're unsure, just simply swap the variables around and then make y the subject. So we had y equals x squared. So how did I get this plus or minus root x? Well, that's what I did. I swapped the x and the y's around. X becomes equal to y squared, made y the subject. I got plus or minus the square root of x. Now, what happens, because we basically sent everything back. So the domain of the relationship becomes the range of the inverse relation. And the other way around is true too. The range of the relation becomes the domain of the inverse relation. If we were to draw both of them on our number plane, they should be reflections of each other in y equals x. So the line y equals x would act like the mirror or the axis of symmetry between the two. So here's a relation. Oh, actually it's a function, this particular one. But we'll draw the inverse relation. Well, there's y equals x. I'm basically going to reflect that in y equals x. So some key points. Well, x-intercepts will become y-intercepts. So we end up with 3 y-intercepts. The y-intercept becomes the x-intercept. So those points are clearly going to be important points. I don't know if you notice how I'm drawing them here. I'm basically drawing a line perpendicular to y equals x. Because y equals x should be the perpendicular bisector of that line, if we were to plot both points in. Whoop, I can pick any point I like. So there we go. This time I've drawn the vertex up the top there. Again, I've gone at 90 degrees to y equals x. And you'll see I've plotted an even distance the other side. So it's a straight reflection. Let's pick another point. Whoop, there we go. Is that enough? Yeah, that's enough. There we go. If you tilt your head 45 degrees, you'll see that, oh yeah, that is a reflection in that line y equals x. Our new thing is not a function, mind you, and that's why we call it the inverse relation, not the inverse function. So what are inverse functions then? If there exists a one-to-one relationship, so what we call a one-to-one relationship between the sets, then the relation will be a function and the inverse relation will end up being a function as well. So when we have that situation, we don't call it an inverse relation, we actually call it an inverse function. How do you test for an inverse function? It will satisfy both the vertical and the horizontal line test. Because if we're reflecting in y equals x, in order for it to be a function, it would have to satisfy the vertical line test. But if we're then going to swap the y's and the x's around, in order for it to be an inverse function, it would have to satisfy the horizontal line test, so that when we do the swapping, the new graph will satisfy the vertical line test. Now, if you haven't got a picture, it comes down to rewriting it with y the subject. So swap the variables around like I did before. If what you end up is unique, if it is unique, then it is an inverse function. Now what I ended up with before wasn't unique because I said plus or minus. So there were two possibilities, not unique. So just to illustrate that, there's y equals x squared. Yes, satisfies a vertical line test, so it is a function, not a problem. But no, it doesn't pass a horizontal line test, so it won't have an inverse function. It'll have an inverse relation, but not an inverse function. Algebraically, that's what I was just saying. Look, it's got plus or minus x. It's not unique. Let's have a look at our very poorly drawn cubic there. Yes, satisfies a vertical line test. Yes, it would satisfy a horizontal line test as well. So yeah, that will have an inverse function. Algebraically, x is y cubed, swap the y's and the x's around. We get y equals the cube root of x. And that is unique because there's only one answer there. So yeah, that's good. That's an inverse function. That's all we'll say for now. We'll on Monday, or it'll be now, we'll have a look at inverse functions in a bit more detail.